Welcome to the course Intermediate Quantum Mechanics. In the last year, in the last semester, in fact, you have attended another course on quantum mechanics, the basic level quantum mechanics. And I suppose in that course, you have learned the preliminary things in quantum mechanics. And let me enumerate the things that I will assume that you already know. That includes, for example, why the formulation of quantum mechanics was necessary, to answer which questions these had to be formulated, then the postulates of quantum mechanics, and then on the basis of the postulates, I suppose you have also handled certain situations where the particle is constrained in what is known as the particle in a box kind of problems. You have done three types of uh, potential functions in which the particle is constrained. You have done the infinite square well, you have done the finite square well, and you have done the harmonic oscillator well. And in doing so, you have obtained certain results. You have seen that energy by itself is not discretized, but it becomes discretized when it is constrained in some kind of a potential well. You have also learned how these can be extended to three dimensions. So three dimensions means the central force problem, the hydrogen atom. These are the things that I'll assume that you have already covered. But in the first class, we will briefly do a recapitulation. What I will assume that you know, but still, nevertheless, I will recapitulate very briefly what I'll assume that you know. You know that the necessity for moving away from the classical pictures, the classical mechanics, classical electrodynamics, arose because of certain observations that included the observation that light, when absorbed by certain vapors, show discrete lines of absorption, which means that energy is absorbed in discrete frequencies, not just any frequency. When light is emitted by something, that's also emitted in discrete frequencies. The question was, why is that? The question was, how do atoms become stable when, as per the classical electrodynamics, the atoms going around the nuclei, which is accelerated atoms, accelerated electrons, accelerated charged particles will emit electromagnetic waves and should fall into the nucleus. Why doesn't that happen? How could atoms be stable? And there are many such observations to explain which the postulates of quantum mechanics were proposed. Now, what are postulates? Postulates are something where, in order to answer a question, the scientist says that I'll make an assumption. I'll make an assumption regarding what is the law of nature. I'll make a guess. But then he says that if that assumption is correct, then I can show that the observed things actually follow of necessity. Take, for example, Newton's law of gravitation. It was an example of a postulate. In order to explain the observed motion of the planets and projectiles, for example, he made the assumption bodies attract each other with a force equal to g m1 m2 by r square. And then he proceeded to show that if I make that observation, then I can explain why the planets move the way they do, the cannonballs go the way they do, and so on and so forth. So essentially, postulates are things, are assumptions, are guesses about the laws of nature. So one should not try to explain the postulates. These are assumptions made by the scientist. But it says that if I make that assumption, then I can show what I want to show. In case of quantum mechanics, the postulates, if I go to the postulates, let me just switch on the presentation now. Okay, so we start with the postulates of quantum mechanics. The first postulate was that in case of classical mechanics, the state of a particle was given by two numbers, the position and the momentum. While in quantum mechanics, the postulate was the state of a particle. This can also be seen as systems of particles. A particle is given by uh, a complex valued function of the position and time. So by a, it's called a wave function, psi x comma t. This wave function contains all the information regarding the state of the particle and everything that you want to know about what the particle is doing from this wave function. That is a basic postulate of quantum mechanics, that the state is given by a complex valued function. Two is that there is a meaning to this wave function, that is the probability of finding. So the particle cannot be localized, you do not know where it is, but you can only talk in terms of the probabilities of the particle being in some range, in some range in space. So that probability, so the probability of finding the particle uh, in the range A to B is that is integral A to B. Now this psi, I'll have to take mod psi square dx. So that is uh, the probability of finding the particle. That is what gives a interpretation of this complex valued function. That means the complex valued function, it's mod square, its magnitude you can say, when integrated over a range gives the probability of finding the particle in that range. And the immediate corollary is that if this is minus infinity to infinity, that means your particle, what is the probability of finding the particle anywhere, is definitely 1, because you must be able to find the particle. So the corollary is that the probability of finding the particle in the range minus infinity to infinity psi x comma t square dx should be equal to 1. And all psi functions that we deal with should satisfy this requirement, which is called the normalization that you have learned. The third postulate is that basically the Schrodinger equation. It is actually a postulate in the sense that Schrodinger did not derive the Schrodinger equation. He guessed the kind of form that nature would follow, and he tested by actually extracting meaningful predictions out of that and then testing that these are true. In fact, the predictions, the observations were already there. He just showed that the equation actually comes out the same predictions. So the Schrodinger is that this is a state. We are interested to know how it varies with time, and that is what the Schrodinger equation gives. The Schrodinger equation says this: uh, the wave function evolves following the Schrodinger equation. The Schrodinger equation. Schrodinger equations, it is I H cross uh, del t of psi x and t is the Hamiltonian operating on the psi, but let me just break it up uh, and write it. So this is H cross square by twice m del 2 del x2, then it will be the psi x comma t. So this is the kinetic energy part, and the potential energy part is the potential energy, some function of x operating on psi x comma t. So the wave function evolves according to the Schrodinger equation. So now it is a kind of function. Sometime later it will be a different kind of function, and how it evolves, that is given by the Schrodinger equation. The fourth postulate is somewhat bizarre. In nature, there are certain things that you can observe, observables, they are called. So all observables, for example, position is an observable, momentum is an observable, energy is an observable, so on and so forth. Angular momentum is an observable. All observables uh, are related to certain operators. Uh, so observables are related to operators. Operators are something that operates on a function like psi and gives another function. Uh, uh, the basic assumption of quantum mechanics is that the psi function itself cannot be observed, cannot be measured. The wave function itself cannot be measured, but what you can observe is actually other observables. And each observable is related to operators. For example, I'll make it a habit of putting a hat on the observable to signify that that's an observable. So x as an observable, its operator is actually uh, as simple as the multiplication by x. Multiply by x. So if there is any function, you multiply that by x, it changes, so it is an operator. The operator for momentum is minus I del x, and so on and so forth. Huh? There are, the moment you have these, you can derive the Hamiltonian operator. Hamiltonian is actually the kinetic energy plus v of x. In this case, this will be an operator, this will be an operator, and this will be an operator. And this p you will substitute here to obtain this. So the point that I'm trying to make is that there is a operator corresponding to every observable, and This is somewhat strange character of quantum mechanics. Observables are related to operators, and the next one is even more bizarre. Uh, every measurement uh, uh, of an observable yields one of the eigenvalues of an operator. Of the corresponding operator. So let me write this correctly. Operator. Operator corresponding to that particular observable. Corresponding operator. Uh, See, these postulates are by themselves strange enough, but that is not all. Uh, if an observable has many eigenvalues, then an observation, a measurement, may yield any of the eigenvalues. But each one is observed with a probability. So there will be a probability of observing the first eigenvalue, the probability of observing the second eigenvalue, and so on and so forth. You cannot predict which one will be observed, but you can predict the probability. And that probability, uh, the probability, so I'm saying I'm not writing, just let me tell that if the observable has its corresponding operator has n eigenvalues, then each one has a probability of being observed. Each eigenvalue has a probability of being observed, and the probability of observing the ith eigenvalue, the ith eigenvalue is I'll say call it pi is equal to uh, integral minus infinity to infinity. Now, here is the issue. I have say the psi function psi of x and t. We will have to obtain its projection, its overlap with the corresponding eigenfunction. Eigenvalue is related to an eigenfunction, so let us call that as say psi I of x. In order to, since we are handling complex numbers, I will have to put then dx. This itself could yield a non-positive number, so this has to be taken mod square. So that is the probability. By itself, this will be the probability amplitude, and when you take the mod square, it becomes the probability. So these uh, are a priori assumptions based on which we have the quantum mechanics structure. The next one is even more bizarre. Uh, is whenever you make a measurement, the act of measurement collapses, instantaneously changes the wave function. It was some kind of a wave function, it instantly changes to another. So which function? A measurement causes a wave function to collapse. Sorry. collapse uh, to the corresponding eigenfunction. So the eigenvalue is the thing that you can observe, and when you make the measurement, the wave function was having was compatible with many possible eigenvalues, and so whenever you make a measurement, the wave function instantly collapses to a specific eigenfunction, the one that is related to that particular eigenvalue. So this is so these 7 postulates are somewhat strange. Some books talk about a few more postulates. Let me write them, but these can be later. It has been shown that it can be this can be derived. For example, if you have uh, uh, if you have a situation where probabilistically various values can be observed, you can either observe one particular value of energy or another particular value of energy and a third value of energy, each with a probability. Then one can surely ask, what is the expectation value of energy? So that is the expectation value of an observable is uh, minus infinity to infinity. What wave function was psi. I'll put star because it could be a complex valued function. Psi star and the psi. Uh, I will put fully. It can be a function of x and t. I'll put some distance, and here is x psi, x and t, and sandwiched between them is the operator. This is called a sandwich integral. This is how we obtain the expectation value of an observable O. And the last one that I'll write is that uh, if there are two observables, so uh, consider two observables A and B, then if the observable A, its operator, and the operator B commute, that is A B minus B A equal to 0, then there is a variable corresponding to A, there is a variable corresponding to B, then the variables, then the corresponding variables can be simultaneously observed or measured. Ideally with infinite accuracy. You cannot really measure it with infinite accuracy, but ideally. Accuracy. But if they do not commute, then the corresponding variables I'll write this way. Cannot both have precise values, which means if they do not have precise values, there is no question of measuring precise values. So you are unable to measure. So it is not really a problem of measurement. It is a problem that actually they do not have precise values if the uh, the corresponding operators do not commute. So notice that we needed so many uh, a priori assumptions in order to explain certain observations. Now, here is something that is uncomfortable about quantum mechanics. Normally, scientists try to attain what is known as economy of assumptions. I assume the minimum number of things, and on that basis, I should be able to explain a large number of events that we observe in nature. But in this case, we found that we definitely needed the first seven a priori assumptions. The last two can be derived from that, but I mean, many people present this as assumptions also. So, so many a priori assumptions where we do not know why these are true is a uncomfortable situation for science. So many scientists, many people who work on quantum mechanics grow accustomed to assuming that these are true. I will advise you to have this discomfiture, because the moment you sort of become comfortable with something, you do not see what could possibly be done to that. And my task is to prepare you for a career in research. So wherever I find that there is a scope of further thinking, I should point that out. And basically, the point is that we do not know why all these postulates are true. We assume them, and then scientists were able to show that if we assume them, then we can explain why certain things happen in nature. And many scientists are uncomfortable with so many assumptions, and they believed that there must be some further underlying reality. If we know that, then possibly these postulates will be explainable in terms of that. Uh, Before I go forward, I think I need to explain the seventh postulate a little more. So I'll just draw a line here and try to explain what this means. It means that suppose at some point of time the wave function is something like this. Uh, Now uh, this function can be shown to be a linear combination. You have learned that in the uh, in the case of the uh, infinite square well, the the first ground state eigenfunction look like this, and the first excited state eigenfunction look like that. The ground state eigenfunction look like this, a sinusoid. A first excited state eigenfunction look like that. And there can be a wave function that is a linear combination of these two eigenfunctions. This eigenfunction is related to the eigenvalue, say, E1, and this eigenfunction is related to the eigenvalue E2. And this is the wave function. Then, if this is a linear combination of these two, actually I'm drawing real valued things. So but you have to understand that these are actually complex numbers. The moment you made the observation, you can either see this value or see that value. It is not guaranteed which value you will see, nor you will see an average value between these two. You will see either this or that. When you measure the energy, you will measure either this value or that value. And what is the probability of measuring this is given by this formula. Yes, this is the wave function and this is the eigenfunction corresponding to that particular eigenvalue, which means this is the wave function psi and this is the eigenfunction psi 1, and the overlap gives the probability amplitude and its mod square gives the probability of observing this value of E1. And similarly for E2. But the moment you have done the observation and you have observed this, instantly the wave function collapses to this. So it was this and it instantly collapses to this. That means it collapses to the eigenfunction corresponding to the eigenvalue that you have observed. Okay, so this is your I'll write a psi 1. Now, if instead you decided to observe the position probability, that means the probability distribution of observing the particle at different places is given by this, if this is your mod psi square. And suppose you have observed it here. It means that instantly the wave function that was like this, see, when you observe the energy, it collapses to this. But when you observe the position, it collapses to something that is consistent with that observation, which means it collapses to this. Now, it cannot be just a delta function because it has to have some narrow width, because when you make an observation, you make it with a finite precision. But the post-observation wave function will be a narrow function like this, but the area under this curve was 1. Area under this curve cannot be 1, so this has to be scaled up so that the area under this can be 1. So that is what a collapse results in. Now, after the collapse, it will continue to evolve from the collapsed wave function. That means it has collapsed to this and it will continue to evolve. And when it continues to evolve, then the logic is that you have to decompose the wave function into the components, the different eigenfunctions, express it as a linear combination of the eigenfunction, and each one evolves. You have learned that when you solve the differential equation, the Schrödinger equation, using a particular v function, the function, for example, the infinite square well, then what did you do? How did you proceed? You assumed that the wave function can be broken up into two parts. One part is dependent on the position and position only. The other part is dependent on the time and time only. So you separated the variables and then solved for each one separately. And when you solved for this, you found that only a certain collection of eigenfunctions can be normalized. The other ones, if you consider that as a solution, then they actually go to infinity at the two sides and they cannot be normalized. Since normalization, that means the area under the curve must be 1, in the sense that the probability of finding the particle somewhere should be 1. and therefore other possible functions are not possible, and therefore other energy values are also not possible. So you found that for the infinite square well, these are particle in a box problems. The energies were given by n square pi square, n is a quantum number, h cross square by uh, twice m l square. Okay, uh, where n is equal to 1, 2, and so on and so forth. And these functions psi n, these you found sine of x. These are only functions of x, where sine n pi x by l. This is what you found. Just to recapitulate what the results were. So for n equal to 1, this was the eigenfunction. For n equal to 2, this was the eigenfunction, so on and so forth. And they evolve, the psi evolves, so each one evolves. So how does psi 1 evolve? Psi 1 each eigenfunction evolves as say psi 1, it will be multiplied by an exponential function which is called the phase factor. It is minus I, the energy of that particular state, t by h cross. So for the nth one, I'll then write n here, en. Now, if a wave function is comprising many such eigenfunctions, each one will evolve according to this. And you can imagine the way it is evolving as sort of, for example, this one, you can hold a thread by the two ends, and you can simply rotate so that it will rotate like this. And that is how, if you look from one side, the complex number, complex valued vector actually rotates. Okay. And you would notice that the rotational speed is given by this. And you would notice this can be broken up into the sines and cosines, and that gives you the omega. And the omega, actually it will be En by t, is different for different wave functions, eigenfunctions. So for the first eigenfunction, its speed of rotation is related to E1. This for second one, it is related to E2, and so on and so forth. So they all rotate at different speeds, and ultimately you have to sum them up. You have also learned about the, I'll just kill this part so that we can get some space. For the harmonic oscillator, so we have also done it for the harmonic oscillator. There you found that the Hamiltonian function, as I wrote earlier, it is minus h cross square by twice m del 2 del x2. This is the operator related to the kinetic energy, plus it was half cx square for the harmonic oscillator. This was the potential function. and it was actually minus h cross square by twice m del 2 del x2. This can also be written as half. C is, it can be written as m omega naught square x square. Both these kind of expressions you will find where your omega naught, the characteristic frequency, is given by uh, and here also your solution, the solution was of the form psi ith, solution was of the form psi I of x. This is psi I of x and t. Sorry, comma t. The psi I x times, again it will be the e to the power minus I e I t by h cross. This is a theme that runs through. And in this case, your E, I, the energy levels are given by n plus half. This is something you learned in the last year. N plus half h cross omega naught. And the eigenfunctions psi n, where sine of x, I'll write it for accuracy, sine of x was some kind of constant, normalization constant, uh, some function of x by a times e to the power minus x square by twice a square. Okay, and the for the ground state, this function is just 1. For the first state is 2x by a, and so on and so forth. So uh, you basically have different uh, wave functions, but it is all these nitty gritty details need not be understood. What in the mind's eye you have to keep alive is that you have the ground state as a Gaussian function. This is a Gaussian function, and in the ground state this function is just 1, so you have got a Gaussian function. This is a ground excited state. It will be just x times the Gaussian function. It will be a function like this. So it goes to 0 asymptotically. All these functions should go to 0 asymptotically. So at minus infinity and plus infinity, that should be actually 0. And the third one would be fourth one would be, you can go on. So this is what you learned in the last year, and you also learned uh, for the infinite square well. This is the dimension of the infinite square well. That means it is ending here. Therefore, at this point it has to be 0. It is ending here at this point. It has to be 0. But if it is a finite square well, then it actually extends. So for the finite square well, it will have two parts. For the finite square well, for example, this one, if this is the location of the, if this is the location of the well, then it would be a sinusoid in this part and an exponential decay here, an exponential decay there. Now, here, these two parts essentially means that the particle has a probability of finding outside, being found outside the well. And is the basis of what is known as the tunneling. So you can have, you can find the particle outside the well and they can go out. So these are the things you learned in the last year. I'll assume that these are the things you know. Uh, in addition, you have learned, I'll just delete this, you have learned uh, the central force problem. Uh, you have learned the three-dimensional, uh, sorry, you also learned the 3D uh, solution of 3D problems. So uh, basically, you have learned it only for one case. Uh, Radially symmetric potential function. So radially symmetric. That is actually true for the hydrogen atom. So you have actually uh, solved the hydrogen atom problem. So this is again something I'll assume that you already know. You know that you have to define certain quantum numbers, and accordingly you have to have a 3D distribution of probabilities. Uh, so all these things you have already done. I'll assume that, and then from that position I'll go ahead. Before I end, uh, I will harp on a an important aspect that you must have learned in the last year. That is, uh, well, how do wave functions evolve? Obviously, it evolves by the Schrodinger equation, but how to picturize that? How to understand that? The point is that if you have well, somebody is writing that you are not comfortable with you have not learned the evolution of wave functions well. So I think I should better take that up in a separate class. Uh, but I can tell you briefly that if you have, uh, say, the way I drew, let us draw the same way. If you have a wave function like this, which is a linear combination of this and that, and this was something like this. I'll better this time, since I'm drawing the second time, I will draw the harmonic oscillator case, which is like this. And the other one would be like this. So these two, the corresponding energy was E1, the corresponding energy was E2. For this particular was psi 1, this particular one was psi 2. I am drawing as a real valued thing, but you have to just keep in mind that these are complex valued. So this one rotates like this in the complex plane, and this one rotates, and this one also rotates. So there are two parts which rotate. This one rotates with a speed that is E1 by, this one rotates with a speed that is E2 by h cross, and so on. Now, the initial condition then psi at 0 was then psi 1 plus psi 2. I cannot really write like this, because even if they are equally, I mean, the strengths are equal, then also this has to be normalized, so I have to write it as 1 by root 2 of this. So that means the probability of finding in this state and probability of finding on this state are the same, and they are 1 by root 2 square, which is half. Now, then you can write psi at x and t as 1 by root 2 psi 1. You have to multiply that by the phase factor e to the power minus I e1 t by h cross, and this is 1 by root 2 psi 2 e to the power minus I e2 t by h cross. Now, this one and this one are not the same. If you consider only this part, that means if you consider only the first one, that means this one can be actually written as, I have probably, I wrote it, but I deleted that. So that will be, if you recall, if I write it again, it was uh, e to the power minus x square by a square. That was the form. There will be some coefficient up front. And it has to be multiplied by the e to the power minus I e t by h cross, e1 t by h cross. So these two multiplied together is the evolution of this one. This one gives the spatial distribution, and this one gives the time evolution. Now, if you want to take psi 1 mod square, then you would notice that this term cancels off and you only get a mod square of this. Because mod square means psi star psi. Star means this will become plus and these two terms will cancel off, giving 1. And so these phase factors do not have any effect on the probability distribution of the particle. But when you have a situation like this, which is a linear combination of two eigenfunctions, then these two are different things and they will not cancel off. I'll show that in the next class. They will not cancel off. And as a result of which, you will see an evolution of the wave function. It's will change with time. And naturally, the probability of finding the particle at different times will also evolve, will change. Okay, so whenever you have a linear combination of various possible wave function eigenfunctions, there is a change with time of the probabilities of finding the particle at different places on the x-axis. I'll better stop now, and we will continue with that in the next class, because you have said that you are not comfortable with the time evolution of wave functions. I will do that and then carry on with the course material of this year. Thank you very much. Let's stop here.